So eigen is a German word that translates to something like own or proper. And the idea is that eigenvectors, they're arrows pointing in some direction, and these are describing special directions of specific importance to a particular linear transformation, or for us, we'll just think in the world of matrices. So these special directions have this property that for a given matrix, the only thing that happens when you multiply a vector in one of those directions is that it gets scaled. It doesn't change direction. It stays pointed the same direction. So eigenvectors are things that are describing special directions for a matrix, or more generally, a linear transformation. And the scaling that happens along those directions is described by eigenvalues. Let's look at a simple example. So I'm going to take a matrix A, 1/3, 0, 0, 2, and think of it as a linear transformation. So I'm going to think of applying it to a two-dimensional vector xy. And if I do that, you can see just generically that the result is going to be that, I'll have 1/3 times x, so that's x over 3 plus 0 times y, and then 0 times x plus 2 times y is going to be the second component. So if we compare this x over 3 2y to our original vector, which was just xy, the difference between these two is that the first component is 1/3 the original length, and the second component is doubled. So if I took a vector that only had a first component and multiplied it by a, the result would be another vector that only has a first component, because there's no y value to double. And similarly, if I took a vector that only had a y value and multiplied it by a, the result would be another vector that only has a y value, right? The x value would be 0, because that transformation is scaling along x independently of how it's scaling along y. So if I start, say, with a vector like 2, 0, so 2, 0 looks like that, and then I multiply it by a, the result is going to be 2/3 0. So that'll be another vector, but it's only going to be 1/3 as long. It's still pointed in the same direction, but only 1/3 as long. And similarly, if I take a vector that's in the y direction and multiply it by a, I'm going to get another vector that's still in the y direction. So if I started, would I start with 0, 1? Yeah. And then the result of multiplying by a would be 0, 2. So the blue direction is shrinking, right? We started with this longer vector and ended up with a shorter one. And the orange direction is kind of growing, right? Things are going to get longer and longer and longer. If I started with 0, minus 1, the result would be 0, minus 2. If I started with 0, minus 2, the result would be 0, minus 4, and so on, right? Things are just stretching, stretching, stretching out along that direction. If I started with minus 1, I would get minus 3. If I started off with a vector 3, 0, I would get the vector 1, 0, and so on, right? And they are the things that I would call eigendirections. And any arrow that points along any one of those things is enough to tell us what the eigendirection is, right? You just need an arrow that shows us which way to go, and that'll describe its span, right? Will give us the entire subspace that is that direction. But so now what happens if we pick values that are, things that are not along one of these two axes, one of these two special directions? Well, then instead of just stretching or just shrinking along the vector that you're starting on, you get more complicated kind of behavior, right? So let's imagine that we start off with the vector 2, 2. And we apply this transformation. Right, so we multiply it by matrix A, and that's going to transform 2, 2 into 2/3 and a 4, right? It divides the first component by 3 and doubles the second component. So this vector 2, 2 gets mapped to, or moved to, however, if you like to think of it dynamically, it gets moved to the vector 2/3, 4. So that's about here. All right, so often it's the case that when we're looking at a direction where things are shrinking, I mean, it seems kind of strange to draw it with the arrows pointed out, because that, like the orange line is right now, it kind of suggests to the eye, right, that things are moving outward along that line. And I mean, really what we're drawing there is the image of this vector is this one, and the image of this vector is that one. When we are shrinking along a direction, it's sometimes useful to just to the eye to say, okay, well, if I had a vector that goes out 3, 0, the result of that is going to be the vector 0 or 1, 0, right? And the same in the negative direction. So sometimes you'll see arrows like this that are indicating that there's a shrinking along that direction. Now, with that in mind, let's see maybe one more example, and I don't want this to get too busy, so I'm going to erase that stuff. I think I would like to start with the vector 9, 1/4. And I want to think of now, instead of just applying this operator, this matrix multiplication just once, I want to do it several times in succession. Because this is sometimes how you see dynamical systems modeled, is by using iterated multiplication by a matrix. And it's something that we'll see in when we do PageRank as well. So this means I'm starting with a vector that looks like that. And then I'm going to apply the transformation. I'm going to apply the transformation once. And if I do that, right, the x-coordinate gets chopped down by a factor of 3. The y-coordinate gets doubled. So I'll have 3 and 1/2. So my next vector is 3, 1/2. That's about here. And if I apply the transformation to that again, I'll get, let's see, 1, 1. And if I do it again, I'll get 1/3, 2. And if I do it one more time, that's going to be the limit of my artistic abilities, I'll get 1/9, 4. So if you think of this as kind of a dynamic process, like iteratively multiplying this starting vector of 9, 1/4 over and over again by A, we start off here, and then you can think of this blue axis that is the direction of the shrinking that's happening, is kind of pulling this vector back down. And if you just look at the x components of all these little vectors that we've drawn, they're getting pulled down exponentially down to the y-axis, down to 0. And at the same time, the y components are getting stretched out away from the x-axis. So you get this really nifty kind of there's like a 100% chance that I'm going to make a complete mess of my picture by doing this, but I'm going to try anyway. I have this nice arc that your system follows as you iteratively multiply it. This one direction is shrinking things down to zero, and this other direction is pulling things away from zero. And in a dynamical systems class, this thing would be classified as a saddle point. This is information that you do not need to retain if you don't want to. I just tell you because it's super interesting. It's called a saddle point because it looks like a manifold that you see in geometry that's called a saddle. Anyway, you see this kind of swoop, right? This pulling pulling vectors away from the collapsing direction towards the expanding direction. And it's really lovely. I encourage you to get on YouTube and find out all you can about that. Also, please share any good links that you find in the discussion because I would like to watch them. All right, so in a nutshell, some matrices have special directions where along those directions, the change made by applying a transformation amounts to nothing more than multiplying by a scalar. So not all matrices have these, but if a real number lambda and a vector v in R, let's say Rn, that's not zero, satisfy A times V is equal to lambda times V, say for matrix A, then we say lambda V is an eigenpair for that matrix A. Let's pick this apart. And maybe I should also say, where did I write it here? That's the lowercase Greek letter lambda. Looks like, well, it kind of looks like that. So for this matrix, the one that we did up here, we had two of these special directions where A times anything that was along the y-axis was just equal to 2 times y. And anything that was along the x-axis was equal to 1/3 times that same vector. So these two things, let's see, this 2 and this 1/3 are eigenvalues. The lambdas, right, are the eigenvalues. And the vectors are the eigenvectors. And together they form an eigenpair for the matrix A. Let's do an easy one and a hard one. But we'll do the easy one first because that's what's going to make the most sense. All right, so let's just think about how to find eigenpairs. We'll start with just values for a matrix A. Well, if matrix A has eigenvalues and eigenvectors, that means that it has some pair, lambda and V, so that this equation, if you can see where I'm pointing, this equation has some way of satisfying it, right? There's a lambda and there's a non-zero vector V. So that's what we got to hunt for. So we must find lambda and V so that AV is equal to lambda V. Now we have an equation, right? And if we have an equation, then we can hopefully do some kind of algebra with it, probably, you know, matrix algebra. And the matrix algebra that you need to do to massage this equation into something that's going to be useful for us works this way. So the first thing to do is to rewrite this in an equivalent way. So I'm going to write A times V is equal to, instead of just lambda times V, I'm going to write it as lambda times I times V. And the reason for that is that over here, A is a matrix. I'm not even going to write that. I'm just going to write that it's n by n. And V is a vector, a column vector. It's n by 1. And so their product is an n by 1 column vector. And without the I here, we just have a scalar times the vector. So it's kind of like we have these two kinds of different objects multiplying on both sides, and just looks a little strange. But if we multiply the identity matrix by lambda, then all of a sudden we have an n by n matrix, right? This lambda times I, since lambda is a scalar, this is just equal to lambda 0, 0, 0, lambda 0, 0, 0, lambda, right? It's just the identity matrix times the scalar lambda. And now when we take the product, we have a matrix times a vector. So we can, and of course we're still going to get an n by 1 column vector as a result. But now we can kind of move these around in a way that's going to be, it's going to be very productive. So I'm going to move everything over to the left-hand side. So I'll have AV minus lambda IV is going to be equal to the 0 vector. And now since I have a matrix times the vector minus another matrix times the same vector, I can use the distributive properties of matrix algebra backwards to like factor out that V vector. So now we have this homogeneous linear system. And that's terrific because we know tons about homogeneous linear systems. And I know everybody, of course, remembers all this stuff. So anyway, so homogeneous linear systems, just to remember, that means we have an m times x equals 0, right? A matrix times a vector, and the right-hand side of your linear system is all 0. Now, these have x equals 0 as a solution, always. And we remember back from like the second week of class or something that if you have a linear system, the number of possible solutions is 0, 1, or infinity, right? So homogeneous systems, because they always have a solution, they always have at least one solution. And when M, the matrix M, has an inverse, then they only have that x equals 0 as a solution. So this is, x equals 0 is a trivial solution. We'll only have a non-trivial solution if M is not invertible. And M is not invertible exactly when its determinant is equal to 0. And that is what we're looking for over here. We want to know, are there non-zero vectors V that work with this? And so we're looking for non-trivial solutions to that A minus lambda I times V equals 0. So our strategy for computing the eigenvalues is going to be to take that coefficient matrix, I wrote it as M over here, but over here it's this whole matrix A minus lambda I. We're going to take that and set its determinant equal to 0. And if we set the determinant equal to 0, then we'll be guaranteeing that if we find a lambda that satisfies this, that can make the determinant equal to 0 when we plug in, we'll be able to find a vector v that's not the 0 vector and is a solution to the system. So let's see how this works. So I'll just write down our plan. So because of this, we will set det of a minus lambda I equals 0 and hunt for lambdas. Okay, so that's the strategy. So then let's start with a not too bad example. I've got this one, 5 minus 2 minus 3, 0. This is our plan, right? We're going to set the determinant of a minus lambda I equal to 0 and solve for lambda. And that's so that we can find a v and a lambda that make that thing work out. All right, so first let's write down a minus lambda I. So we're going to be subtracting from our matrix A the matrix that is lambda times I, right? So that's just the matrix that's got lambdas on the diagonal and zeros everywhere else. So A minus lambda I is always whatever your A is. It's just exactly that, except there's minus lambda accompanying every element on the diagonal, every entry on the diagonal. The last one is 0 minus lambda. And so now we're going to take the determinant of that and set it equal to 0. Okay, so we compute this determinant. We're going to get 5 minus lambda times minus lambda minus negative 2 times negative 3 is positive 6. And if you work this out, we get lambda squared minus 5 lambda minus 6. And just while I have one of these up, this thing right here is called the characteristic polynomial. And when you add the equal sign to it, then you get the characteristic equation. So people will talk about finding the characteristic polynomial and setting it equal to 0. This is what they're talking about. Okay, so this is not too hard a quadratic equation to solve. So this will just be lambda minus 6 times lambda plus 1 equals 0. And so now we see that there are two different values of lambda that will make it so this, let's go back here, we'll make it so that this equation has, so I'm pointing at this equation has a non-trivial solution. Remember, this always has the solution v equals 0, but we're looking for non-trivial solutions. The only time we'll be able to find a non-trivial solution is when this determinant is equal to 0. And what we've just discovered is that for our A, this one over here, there are exactly two values that when you plug them in for lambda, and that expression will result in a matrix that has determinant 0. And now for each one of those, we need to find an accompanying direction, right? We need to find an accompanying eigendirection. So now that we have found our eigenvalues, so that's lambda, I'll call it lambda 1 is 6, and the other one is negative 1. And now we can find the associated eigenvectors. Right? So for lambda 1 equals 6, we want to find the eigendirection that goes with this one, this scaling factor of 6. So that means that we're looking for the direction that will make this true. So what vectors have this property? And again, I guess I can write our A down again. Our A was 5 minus 2 minus 3, 0. Right, so if we're looking for the vectors that when we multiply them by our matrix, we just get the same vector again, but stretched out by a factor of 6. All right, and to answer this question, again, we're going to take everything over to the left-hand side. So this is an AV equals lambda V. If we pull everything over to the left-hand side and stick in the identity matrix so we can factor things out, we're going to have, you know, I'm talking about this A minus lambda I times V equals 0. If we do that, we're going to have 5 minus 2 minus 3, 0 minus lambda I. Let's see, lambda is 6. So it'll be 6006 is lambda I times V equals 0, right? So we just have our homogeneous system. And by design, right, we found these values lambda so that we would guarantee that there is a non-trivial solution to this system. All right, so if I solve this, let me first simplify it. So 5 minus 6 is -1, and then they have -2, -3, and -6 times V is equal to 0. And I think that you can see that just a single row operation, like if I do row 2 minus 3 row 1, is going to take us to basically exactly where we need to be, to get our general solution. Remember that we're expecting this to have a free variable. All right, and let me call this V will be little v1, little v2, I guess. So we'll have, reading off this equation, I have minus v1 minus 2v2 equals 0, and 0 equals 0 is the other equation. And so I see that together these tell me I've got v1 is equal to -2v2, and v2 is free. And now, since that's the case, our general solution to this homogeneous system is this. It's minus 2v2, v2. And that general solution represents all of the vectors that point along this direction. I just need something simple that can specify this direction. So I just need a simple particular solution. Hey, sweetie. Working? Yeah, I'm having a lecture right now. Do you want to say hi to my class? You don't want to? All right, bye. So a simple particular solution is just one that we just can plug in anything we want, but not 0. 0 doesn't point anywhere. I mean, the 0 vector doesn't point anywhere, so that's not helpful in telling us anything about the direction that we're looking for. But I think that if I set v2 equal to 1, I'll get a nice simple vector, -2, 1. And that's what I'll take as my eigenvector that's going to specify the direction that gets stretched by a factor of 6. Okay, so this is our first eigenpair. And when I see that this is an eigenpair, I already have a partial picture of how this linear transformation treats vectors. So this vector v1 describes the direction, right, by saying, okay, let's see, -2 and then 1. Oops. And then 1. So that is the vector that I've written down as v1. Again, any vector that points in that direction is an eigenvector. I just wanted to pick something that was fairly simple. So this tells me the fact that this is an eigenvector that I found this way and that the eigenvalue associated with it is 6. It tells me that if I pick any vector along this line and I apply that matrix to it, right? I multiply it by 5 minus 2 minus 3, 0. If I plug in anything that's along this line into this expression, I'm just going to get something that's the same direction but 6 times longer. So in other words, I guess that looks about 6 times longer, maybe not quite. And that's true for components of vectors that are in that direction as well, components of other vectors. Now, that is one eigenpair. We had 2 eigenvalues, so we have another one that we need to look for. The other one was lambda 2 was equal to -1. So a minus -1, so a minus lambda I, right? That's going to be equal to, in this case, 6 minus 2 minus 3, 1. Okay, so if we work this one out, again, you can see like one row operation. Let's see, I think if I do row 2 plus half row 1, we'll get rid of that whole second line. And then we'll be left with just 6 minus 2, 0, 0, times the vector v is equal to 0. The general solution, if you work it out, is that v1, so the first component, is equal to 1/3 v2. And again, I'm not interested in having this whole general solution. I just need a simple particular solution. And 1 is always a very nice, easy number to plug in. But in this case, since there's a fraction there, I'm going to plug in a 3 for v2 so I can get rid of the denominator. So v2 is set to 3. Then my eigenvector will be 1, 3. And that's going to be my other eigenvector, is 1, 3. So now that tells me something also about this transformation. So if I look at, let's see, this other direction that's an important direction is described by the vector 1, 3. So that's about here. You have to forgive me for not labeling my axes, but it gets too cluttered when I'm trying to talk. And since I'm here to tell you that every one of these boxes is 1 unit, then I don't have to write it down. All right, so that's the line, right? The subspace that's specified by 1, 3. And the fact that this, this value, the eigenvalue associated with it, is -1 tells me that, well, what happens if you multiply a vector by a scalar -1? Well, it stays the same length. It just flips to the other, to be in exactly the opposite direction. Say I take a vector that looks like this along that direction. The fact that this eigenvalue is -1 tells me that if I multiply a times v, I'm going to get -1 times v. Right? So that matrix is not going to take my little pink vector off of that orange line. It's just going to flip it to the other side. Same length, just pointed the opposite direction. And now, so if I take an arbitrary vector that lives out here in R2, that's not on either one of these lines, like this, the component of this vector that is in the orange direction is going to get flipped across that other line. And since this green direction scales by a factor of 6, the component of this vector that's along that direction is going to get multiplied by 6. So our resultant vector is going to be flipped to the other side of this green line and is going to be quite long, right? Because it's going to be the same kind of distance away from the green line, just in the opposite side, and it'll be 6 times as long as it is according to the green line. So those are our 2 eigenpairs. That's something that they can tell us about in terms of like how the linear transformation behaves. All right, so in this one, our matrix A is going to be a 3 by 3 matrix. It's going to have a lot of zeros in it though, so that the computations aren't too unmanageable. Okay, so let's figure out what's going on with this matrix. Let's find the eigenvalues and eigenvectors, and then we'll see if we can interpret them somehow. So we start off by finding the eigenvalues. We have to do that first so that we can set up those homogeneous linear systems, and find those general solutions that have different, non-trivial solutions. So we'll start by finding the eigenvalues. So we're going to set the determinant of A minus lambda I equal to 0 and solving for lambda. All right, so first, let's write down A minus lambda I is going to be, let's see, this will be 1 minus lambda, 0, 1, 0, 2 minus lambda, 0, and 0, 1 minus lambda, because 0 minus lambda is just minus lambda. And now we need to compute the determinant of this. I see that there's this one column. This one column has only one non-zero entry. So I'm going to do cofactor expansion along that column. You are free to find the determinant in whatever way you prefer. But let's see, the grid is plus minus plus minus. So this is plus, of course, because it's first. So this will be 1 minus lambda times the determinant of this submatrix, right? So we'll have 1 minus lambda times 2 minus lambda times minus lambda minus 0. Oh, that's nice because this is already factored. So let's see. If I take this minus sign and put it with that one, then I'll have lambda minus 1, and 2 minus lambda equals 0. So our eigenvalues are the solutions to these, and we have 3 of them. Lambda 1 equals 0, lambda 2 equals 1, and lambda 3 equals 2. All right, so when you have a 3 by 3 matrix, in general, you're going to get some kind of cubic polynomial for your characteristic polynomial, and those can be really, really hard to solve. So, I don't know, just be prepared for that. And find a good online polynomial solver. Okay, so we've got these 3 eigenvalues. And now we're going to set up our homogeneous systems to find the corresponding eigenvectors. So let's see. So let's start with lambda 1 equal to 0. So now we're going to have A minus lambda I. Our lambda is 0. Happens to just be equal to A itself, right? Because the eigenvalue is 0. So our A minus lambda I is just equal to A. So we just have this homogeneous system to solve. So we've got 1, 0, 1, 0, 2, 0, 0, 1, 0 times our eigenvector is equal to the 0 vector. And I think you can see if I just did one row operation that said, let's see, let's do row 3 minus a half of row 2. That'll get me to this system. 1, 0, 1, 0, 2, 0, 0, 0, 0. Oops. And if I read off the equations so that I can solve this system, I see that I have the first one says V1 plus V3 equals 0. The second one says that 2 times V2 equals 0, and that means straight away that V2 has to be equal to 0. And the first one just means that V1 has to be equal to minus V3. And V3 is free. That good to everybody? If you have a question, please ask it. All right, Theodora's okay. Peter, do you have a question? Okay, good. Anybody else want to, I mean, I can call on you by name, force you to answer me, but I guess you'll ask a question if you aren't happy. And all we've really done is solve this to get this general solution for this homogeneous linear system. So this general solution is now this. So we have minus V3, 0, and V3. And I just need one particular solution, right? That's a simple one will do. So I'll just pick V3 equals 1. And that's going to be my first eigenvector. Will be minus 1, 0, 1. Because you could pick anything you want. I mean, if you picked V3 to be equal to negative 1, then your vector would be 1, 0, minus 1. Maybe that's simpler. It doesn't matter. So that's 1. And then we have 2 more. So let's see, lambda 2 is equal to 1. So in this case, our a minus lambda I is just a minus I. And that is, let's see, looking back up at the matrix, that's going to be 0, 0, 1, 0, 1, 0, and 0, 1, 0. V is equal to the 0 vector. And you can see again, if I just do one row operation, R3 minus R2, that's going to get me to this linear system. You'll notice that I'm not like being super worried about echelon form and all that stuff. All I'm really after is the solution to this. If I can see something that's going to save me time doing this by hand, perfect. Okay, so now what does this tell me? This tells me that x3, oops, sorry, I've been using V's. It tells me that V3 is equal to 0. And the second row tells me that V2 is equal to 0. And the third row tells me nothing. So it looks like V1 is free in this one. So that means our general solution, if you like to write those down, is V1, 0, 0. And so I'll take as my second eigenvector, you can probably guess, I'll take 1, 0, 0. And then we just have one more. Lambda 3 is equal to 2. And if we compute then lambda, a minus lambda I, so that's a minus 2I. Everybody's bailing, but the interesting part is the interpretation of this, which is what's coming next. We just have to find the last one, and then we can talk about the geometry. Okay, so we'll have minus 1, 0, 1, 0, 0, 0, and 0, 1, minus 2 times V. is equal to the 0 vector. All right, and so I don't even need to do any row operations, right? I already have a row of all zeros, so I may as well just write out the equations. The first one is going to tell me that V1 is equal to V3, since that first equation has to be equal to 0. And the last one tells me that, let's see, V2 is equal to 2 times V3, and that V3 is free. So our general solution is V3, 2 times V3, and V3. So the simplest solution, the simplest particular solution, I think, is probably 1, 2, 1 by setting V3 equals 1. And so that's our last pair, our last eigenpair. And now we can think about like what is actually happening here. So let me, I'm going to just be a little bit lazy and just copy these things. There we go. All right, so these are our 3 eigenpairs for this linear transformation. And since we're in a 3 by 3, matrix situation, that means we're living in 3-dimensional space. And there are these 3 dimensions that are specified. So I'm going to write down the second one first. I think maybe I will use green for that one. So this is our second eigenpair, and it says that along the direction 1, 0, 0, oh, I should probably label something here, right? This will be x1, x2, and x3. So along the direction 1, 0, 0, anything that you apply the transformation to doesn't get changed direction-wise. And because the scaling factor is 1, it also doesn't get changed lengthwise. Everything that's along this direction is absolutely fixed. So vectors on the x1 axis are completely fixed. Now, the next sort of simpler one to think about is this one. So every vector that's along the direction 1, 2, 1, right, along that direction, is going to be exactly doubled in length. It won't change direction, it'll just double in length. So if I look, where's 1, 2, 1? So 1, 2, 1. So that's a vector that's pointing out here. And so it goes back in that direction, comes forward up here. And anytime you plug in something to that operation that's along that direction, it's just going to exactly double in length. I wish I could draw 3-dimensional pictures better than this, but this is as good as it gets. Just close your eyes for a second and imagine what it looks like. But the most interesting direction, I think, in this one is the one that comes from, oh, whoops. I was going to write down that vectors on this line that's determined by the vector 1, 2, 1, double in length. But the most interesting one, I think, is the this first eigenpair. So that direction, let's see, -1, 0, 1. So that is in the x1, x3 plane. There's its span, that vector. If we write down what our matrix equation is for these vectors, right? So A times V1, or anything pointed in the direction of V1, these are the vectors that have the property that they're equal to lambda 1 times themselves. But in this case, lambda 1 is 0. So 0 times any vector gives us the 0 vector. So that means that any vector at all that's along this line in the x1, x3 plane, it's going to get mapped down to 0. It's going to get completely squished. So that tells us some interesting stuff, right? So for one thing, it tells us that lots of different vectors get mapped to the same vector. There's an infinite number of vectors along this orange line, and if I apply that transformation, I get the same output every time. It's 0. Right? So the span of this thing is actually the kernel of the linear transformation that is associated with this matrix. Right, so this is a big deal, right? The kernel of that linear transformation AX is the span of the eigenvectors associated with eigenvalue 0. We didn't use the word kernel. We used the word null space, right? Is that right? Is anybody still listening? Oh, okay. Okay. Yeah. Okay, good. So the null space of T of X equals AX is the span of this vector minus 1, 0, 1. And everything that's along that direction is getting squashed down to 0. In fact, the range is the span of these two vectors that are associated with eigenvalues which are not 0. So let's see. If I mixed purple and green, what would I get? Brown, I guess. Let me just stick with green. So the range would be the span of 1, 0, 0 and 1, 2, 1. Right? And that's because their span is everything that's not along that other vector. Those directions grow or stay the same size. Okay, so anyway, that was my harder example that I wanted to show.